So in section 5.2, it's titled Exponential Models. We're going to start by rewriting exponential functions to identify rates. We're going to interpret parameters of exponential functions within the context of compound interest problems, and we will construct exponential models given 2 points. So the first set of that description, we're going to rewrite each function to find a monthly growth rate. So when I'm looking for my monthly growth rate, it's important for me to remember that there are 12 months per year. And so I'm going to use that relationship at some point within the problem. So we're given population problems. So if I think about this, both of these, so since I see that word growth, that means that I'm going to look at an exponential growth model. So remember that that means that for this problem, we're going to be looking at y equals our initial amount times 1 plus our growth rate raised to the t power, where t is in years. And so we will be given the A and the R in the problem, and then we're going to manipulate to figure out the growth rate. So we're going to kind of manipulate an equation and then go backwards to find a new rate. So in 2015, so that's going to be our starting year, the population of a small town was 8,000. So they're telling us that our starting amount is 8,000. And then it's increasing at a rate of 2.5% per year. So our rate is 2.5%. Remember that we always want to change a rate to a decimal. So that means that we're going to move our decimal 2 spaces to the left. So it's going to become 0.025. Okay, so that means that our population can be estimated using the formula y equals 8,000 times 1 plus 0.025 raised to the t power. Okay, so if I simplify that, we get 8,000 times 1.025 raised to the t power. So since I'm looking for this monthly growth rate, I am going to multiply my exponent, which is t, by 12 over 12. Remember, 12 over 12 is really just 1. So I'm going to just put 12 over 12 as a coefficient on t in my exponent. So I still have everything else the same. I just have 12 over 12 as my exponent. So that's the first thing I'm going to do in order to manipulate my equation. So I'm going to use power of a power, which is one of our exponent rules. And I'm going to split it into 1 over 12 times 12. So remember that if I had an exponent inside here, so I'm going to raise my 1.025 to the 1/12th power, and then I'm going to keep my 12 out here with the t. So I'm going to find the growth rate this way. If we think about that, because there's 12 months in a year, if I plug in the number of years, 2 years, my exponent will be the amount of months within there. So that's where this is coming from. Then what I want to do is I want to evaluate my base. So evaluate the new base, which means I'm plugging into my calculator 1.025 raised to the 1/12th power, and I'm leaving everything else. So 1.025 raised to the 1/12th power is going to give me 1.025 as my base. Okay, so now if I remember, I now have this simplified equation. Okay, so this, when I plug in the number of years, will be an exponent of how many months. And so what I'm going to do is I'm going to use this to find my growth rate. So remember that this is my 1 plus my growth rate. So let's take that and find this here. This is a little tight, I'm sorry. It'll be better for the next one because we won't be writing the steps. So we're going to do 1 plus our growth rate equals 1.00206. So then I would just subtract 1, and that will give me my growth rate. So R is equal to 0.00206. And if I convert that back to a percent, that means that my monthly R is equal to 0.206%. Okay, so the monthly growth rate of the population is 0.206%. Okay, so as we do B, I'm going to kind of just focus in on the part that I need to answer the question. So if I were to need to figure out the amount in the population after a certain number of months, I can use this equation that we found here. However, the question's just asking us for this monthly rate. So all that I really need to get that is this piece of that equation, okay? And so if I know that this is the process to write a new equation where T is in months, then I can just take this piece and use that idea to find my monthly growth rate if I'm given an annual rate. So I'm given this function, they're giving me the A value and the B value. So remember that A was our initial amount. So maybe we're investing $1,500. And then this is the base of our function. Did I use a color? I made that, let's see, I made that blue here. So we're gonna call that B. So B is 1 plus R, right? And so I can see from here that the original growth rate, the annual growth rate is 1.2% or 0.012. So what I'm going to do is I'm going to take that number, so my 1.012, like I used 1.025 here, and I'm going to raise that to the 1/12th power because there's 12 months, right? So I'm going to just work with that piece that I need. So I've got 1.012, and I'm going to raise that to the 1/12 power. So if I look at that in a calculator, so if I type that in, that tells me that my value for B, if I'm looking at it with a monthly rate, would be 1.00099. Okay, so if I type in 1.012 and raise that to the 1/12th power, I get 1.0099. Okay, so if I think back to what we did, we subtracted 1 from our B to get our monthly growth rate. Okay, so we've calculated for the months. So now if we look at what we did from the original problem, our last step was to subtract B minus 1. So if our B is now 1.00999, and we subtract 1 from that, that leaves us with a new R value of 0.00099, which means, so remember, if I'm going to percent, I'm moving my decimal to the right now. So to go from a decimal to a percent, I'm moving to the right 2 spots. So R is 0.099%. So that's my monthly growth rate. Okay, so without having to do the whole equation, because I don't need to know the population without as many months, but I would use this setup otherwise. So I would put a 12 with my exponent if this is my new b. Okay, so I could go back to the original problem and say then my f of t would be 1,500 times 1.00099 to the 12t power if I needed to calculate that. Okay, so compound interest is a special form of a growth function in the instance where interest is added or it's growing at a certain rate. So when interest is paid monthly, it's earned after the first month becomes part of the new principal for the second month and so on. So it's compounding, it's getting added to the balance. And so you're increasing more money each month as opposed to just making the same amount of interest each month. So the compound interest formula is an exponential model that's used to calculate the value of an investment when interest is compounded. So P is the initial principal that's invested. So P stands for principal. It's something that's used in banking. And then R is our annual interest rate written as a decimal. N is the number of compounding periods per year. So if that rate is compounded quarterly, for example, that would mean N would be 4 because there are 4 quarters in a year. Monthly would be 12, yearly would be just once. And then N is the number of, A is the value of the account after T years. So our total value is A, the amount in the account. So we're going to use this formula to figure out the amount after 3 years for Tamira, who invests $5,000 in an account that pays 4% annual interest. So they're telling us that her principal, right, the amount that she is initially paying, so her principal is equal to $5,000. And then the rate is 4%. Remember that as a decimal, that means it's 0.04. So that's the value that we'll use. And then how much will there be in the account after 3 years? So T is 3. If the interest is compounded annually, semi-annually, quarterly, or monthly. So I wrote these values across the top because those are not changing for the problem. However, the compounding rate is. So if something is annual, that means that N is 1. It's only happening once a year. If it's semi-annual, that means that N is 2. It's happening twice a year. Quarterly, we already said, means N is 4. 4 times a year, and then monthly, there are 12 months in a year, so N is 10. So these are some pretty standard N's that you'll see within a problem. If we think about like daily, it could be, that would be 365, right? Because there's 365 days in a year. So we're going to plug each of these pieces into this equation. So our amount in the account is equal to the principal, so 5,000 times 1 plus the rate over N raised to the N times T power. So our rate is 0.04. And then that's raised times to the N times T power, where T is 3. So I just filled all those in so that I don't have to write it each time. So we can pause when we need to. So N is 1 for this one. So N goes in my denominator and N goes here, okay? N is 2 for semi-annually. So 2 goes in the denominator and 2 goes here, okay? Quarterly, N is 4, so I'm dividing by 4 and multiplying my exponent by 4. monthly, I'm dividing by 12, and then I am multiplying by 4. So if I think back to what we just did in the previous problems, notice that this formula accounts for what we were doing. So this is how we were kind of connecting the two. So what I suggest that you do, just because all calculators are different. So if you're using Desmos, you can type it so that it looks exactly like this. If you're using a handheld calculator, it's a good idea to evaluate this separately. So meaning if I were to plug in 1 plus 0.04, I would get 1.04 and kind of simplify. So I'd be doing 5,000 times 1.04, and then 1 times 3 is to the third power. Before I evaluate. So then I would type this into my calculator and I would get $5,624.32. So again, if I'm using Desmos, I can type it in exactly like this and go straight to the answer. If I'm not, I suggest you evaluate this first. So 0.04 divided by 2 is going to be 0.02. So we're going to get 5,000 times 1.02 raised to the 2 times 3 is 6th power. Okay, if I think about this, 0.04 divided by 4 is going to give me 0.01. So this is going to be 5,000 times 1.01 raised to the 12th power. And then 0.04 divided by 12 is actually 0.003 repeating. So this is equal to 5,000 times 1.003 repeating raised to the, oops, I wrote a 4 there. That should be a 12. And then 12 times 3 is 36. So that'll be to the 36th power. Okay, so if I evaluate each of these, so again, type in 5,000 times 1.02 raised to the 6th power. That's going to give me $5,630.81. Notice that if I'm compounding interest one more time a year, I'm making a little bit more money on my investment, right? So that interest is getting added back to the account, and then I earn more interest on it. So the more it's compounded, the kind of more money you make. So these should increase based on that nature. So if I type that into my calculator, I get $5,634.13. So then if I do it 12 times a year, I get, $5,636.36. So notice that the more times the interest is calculated, the more money I make. Okay, so what happens when the interest is always being compounded? So every second of every day you're making money off of your principal, there's a formula for that. So the number E is the base in the continuously compounded interest formula. So the value for E is the natural base. That's about 2.72. So it's an irrational number like pi, where it's not predictable and it's not repeating. So the numbers just keep changing and changing and changing. So that's the only piece that's changed, right? So instead of having an N, we have E, and that's just a value. So this formula is a lot easier to use. You're just really plugging things into your calculator. So Regina invests $12,600 into an account. So that's her principal. Her starting amount is $12,600. That earns 3.2% annual interest. So our annual interest rate is 3.2%, which means 0.032. Compounded continuously, I'm going to highlight that. That tells us that we're using the formula A per. So A equals P times E raised to the RT power. Okay. So A is asking us, what is the value in the account after 12 years? So T is 12. For B, it's asking us for 30 years. So P and R are the same. We're just evaluating for a longer period of time. Okay, so for A, after 12 years, we're doing 12,600 times E raised to the 0.032 times 12 power, which means we're doing 12,600 times E. So if I multiply those two together, I get 0.384 power. And so that gives me about $18,000, $18,498.63. So this button E usually is with a button LN, like you usually see it at the top here. So it'll look like that. So that's the natural log. So you'll have to either hit like shift or second, depending on what your calculator is, to get that E there. Okay, so then if I'm changing this, so that's my answer for A. I need to find this for when T is 30. So the only thing that's changing is that my exponent is going to be 0.032 times 30. So I still have 12,600. My base is still E because it's still compounding continuously at a rate of 0.032. And then we want to see what happens after 30 years. So that means we're going to multiply 12,600 times E raised to the 0.96 power. So if we calculate that, we get $32,907.38. Okay, so without investing any more money at that rate, her $12,000 has turned into $32,000. Okay, so the last concept is when we are given points, we're going to write an equation. So given the points 6, 1,000, and 7, 1,400, write an exponential equation to model the situation. So let's go back to what we know about exponential models. And so that's that they're growing at this constant rate, okay? And so what we're going to do is think about this in terms of the X and Y values. So I left some space on purpose. So my X value at 6 is 1,000, and my X value at 7 is 1,400. My line doesn't need to go all the way over there, but I need the space. So what I want to think about is my change in X, which means what am I adding or subtracting to get the next X value, which in this case is 1. Okay, so this needs to be 1 for this to work. So then what I want to look at is my ratio of my Y's. Meaning, if I take my second point, my 1,400, and I divide it by my first Y value, which was 1,000, what do I get? So in doing that, 1,400 divided by 1,000 is 1.4. Okay, so what this means is that for each X value that increased by 1, I would get the next y value by multiplying by 1.4. So for example, like if I were to find 8, right, I would add 1 here to get 8. Then I would multiply times 1.4 to get my y. So that would mean I would take 1,400 and multiply that times 1.4, which would give me 1,960. So I can find those values like that. So this question is asking us to write a model. And so what we can do with this is think about what we know. So we know that an exponential model is y equals a times b to the x power. Okay, so b is our ratio of our y. So b is 1.4. A, remember, is our initial amount always. And so I can't find that until I know something about the points. So what I'm going to work with is I don't want to go all the way back to 0, right? I don't want to subtract 6 and figure out what this is. So this a value is actually what is y when x is 0. So what I'm going to do instead is I'm going to use my point 1400 to find it. So this is my x, this is my y. I'm going to plug them in. So I've got 1400 equals a times 1.4 raised to the 7th power. Okay, so I'm using my point x, y, and my b to figure out a. So remember that if I had a point on the table whenever x was 0, the y value would be my a. So I don't want to go all the way back and keep subtracting, and then I would be dividing until I get that 6 times. So what I can do instead is take 1400 is equal to a times 1.4 to the 7th. If I calculate 1.4 to the 7th, I'm going to move that to become a coefficient. So 1.4 raised to the 7th power is 10.5414a. Okay, so I'm just rearranging that to be a coefficient. I would then divide by 10.5414 on both sides to determine the value for a. So if I divide 1,400 by 10.5414, that's going to give me an a value of about 133. Okay, so I'm going to round that up to 133. So if that's my a value and my b was 1.4, I want to plug those two in. So y is equal to a was 133 times b was 1.4 raised to the x power. Okay, so my answer is that. I chose the last point. Just note that I could have used 6 and 1,000 as well. So they'll both work, but I have to identify the value for b and then plug in x, y, either one, and a b. I could have even used my new 1960. And then that will allow me to solve for a, and then my answer has that a value and then our b as the base.